All right, welcome everyone to a new episode of the Roscoe's Wetsuit Podcast. I am your host, Toby Passman. On the show with me today, we have a very special guest, Dr. Robert Thatcher. Dr. Thatcher received a BS degree in chemistry from the University of Oregon, go Ducks, and a Ph.D. in biopsychology from the University of Waterloo. He's the developer of NeuroGuide software for QEEG and Neurofeedback and is the author of over 200 publications, including 8 books. His most recent books are the Handbook of Quantitative Electroencephalography and EEG Biofeedback, along with Z-score Neurofeedback Clinical Applications, which he co-edited with Dr. Joel Lubar, who's been a previous guest on the podcast. He's currently the director of the Applied Neuroscience Research Institute and the president and CEO of Applied Neuroscience, Inc. Dr. Thatcher, welcome to the show.
Well, thank you, Toby. I appreciate it.
Yeah. So maybe first off, just for our listeners who aren't, within the field of, sort of EEG, QEEG, neurofeedback, can you just sort of break down what maybe, because I've talked to some people and brought up EEG and neurofeedback several times on the podcast, but can you sort of explain QEEG, what a quantitative electroencephalography is?
Yeah, sure. Well, a good way to start is to recognize that the brain weighs about 3 pounds and consumes 20 to 40% of our blood glucose. That disproportionate amount of energy goes into creating electricity. And so that electricity is what we call the EEG. And the EEG is just simply the synchronous activity of the 100 billion neurons, or a little bit more than 100 billion, that coordinates everything we do, from all of our hopes, our dreams, our projections of the future, our movements, our emotions, our cognitive analytical capacities, etc. All of that is being done by this 3 pounds. Of course, it's also connected to the immune system and to our heart. So there's both biofeedback of like heart rate variability and the EEG are useful. But the key here is to focus on that organ. Now, I worked at the National Institutes of Health as a project manager for the first 128 channel EEG. That was in 1990, it's about 1994. And that was the first decade of the brain that George Bush I created, and $2 billion went into that program. And that time, we got together as a group of us. I was also involved in co-registration of EEG and MEG, that's magnetic electroencephalography, with PET scans, SPECT scans, and structural MRI. This is before functional MRI came into being, and also before diffusion denser imaging, a few other imaging methods. And as in the course of, well, first of all, we came up with a coordinate system, which is called the Taueric Atlas Coordinate System. We had a variety of discussions because we had to have a way to co-register these modalities. And that coordinate system is a way to scale different size brains and get, because there's landmarks in the brain you can identify, they're called the anterior posterior commissures. These are big fiber bundles. You draw a line between them, and then you divide the brain up, essentially put it in a cube, so it has an upper and lower hemisphere, left and right, and a coordinate of 0, 0, and near the hypothalamus. It's called the Descartes point. But then now there's 3-dimensional coordinates for all the parts of the brain. That's also in for all the voxels of the MRI, all the sources of the EEG, all the changes of blood flow in the PET scan, all co-registered to the same coordinate system. That became the standard in 1991. Shortly, well, in 1991, we started to see that even though there's 100 billion neurons, there's a small set of clusters that get active synchronously in particular areas of the brain that have different functions. Like the occipital lobe's involved in vision. And so temporal lobe's involved in auditory information processing. The motor cortex is involved in movement. So there's different parts of the brain that do different things. And they have, these parts of the brain actually physically are different. They have different cytoarchitecture. This guy, Copian Brodmann, in 1904, around there. He did autopsy analyses of human beings and monkeys. He evaluated the cytoarchitecture of the different parts of the brain, and he saw and he cataloged these different, the way the neurons are actually different. The Brodmann area 1 is called it 1. Is where he first saw it different from Brodmann area 2. Brodmann area 1 is essentially the motor cortex. And then Brodmann area 2, I can't remember it. I think it's that cortex is the sensory cortex is next to it. And so he went Brodmann area 1, 2, 3, and each of these areas, he came up with 44 areas on the left hemisphere that have unique cytoarchitecture, and 44 on the right. And this is right at the period of Darwinianism, where structure and function were the main theme. Now, neurology and psychiatry had not split apart at that time. So he basically was he's a neuroanatomist, neurologist, before neurology was a formal discipline. And he confirmed that a lot of that also was in monkeys. So even though there's 100 billion neurons, they're actually organized in 88 hubs, clusters. Those were all confirmed at NIH in PET scans. Over 30,000 PET scan studies were done. The first decade, 2 billion, that's essentially what happened. And then the second decade is another 2 billion. That's where the connectome was developed. We can go from 3-dimensional hubs to a 2-dimensional map, so it's easier to work with it. So Brodmann was resurrected. And so that's when we discovered the brain is actually made up of networks, hubs with connections. The second decade of the Human Brain Project went into the details of that connectivity, looking at different densities of connections. Certain, like the amygdala is a higher order part of the brain. It's connected to a lot of places. The anterior cingulate gyrus is another part. It's part of the limbic system. It's higher order. It's connected to a lot of other places, or not connected to a lot of other places. The temporal lobes, for example, tend to have a smaller number. So they got categorization of the hierarchy of the hubs. And then you could link the dysregulation of the hubs to symptoms. You would see people that have anxiety disorders, then the anxiety network would light up in the PET scan. If you have attention disorders, you have both a dorsal and a ventral attention network, so there's different parts of attention, and those hubs would light up in the PET scan, etc. So linking patient symptoms to dysregulation in the hubs became the main theme in the first decade of the Human Brain Mapping Program, and then it continued. So I published 2 large volumes there at National Institutes of Health to help organize conferences. We brought people in all around the world. We were dealing with PET scans and some later on functional MRI, SPECT scans, EEG and MEG, and we're able to show it, co-registered everything. So that became the foundations. Now, EEG has the advantage it's in milliseconds. PET scan takes 20 minutes. Functional MRI is 20, 30 seconds. So EEG and MEG are the only imaging methods that can really measure the time domain, how fast different parts of the brain talk to each other, what factors determine the delays between, let's say, the occipital lobe and the frontal lobes, or the parietal lobes and the frontal lobes, etc., which basically is because everything is connected through the white matter. There's conduction velocity. So the greater the distance between any 2 hubs, then the greater the phase difference. So you can measure the time differences and the phase differences in EEG that correspond to the underlying physiology. Also, the rise time of synapses and the synaptic delays, they contribute to the phase delays. So the phase delays became very, very important because it's linked to the underlying neuroanatomy. It allowed us to then correlate structural MRI with EEG. And also now there's 2 categories of structural connectivity. There's functional connectivity and affective connectivity. There's 3 kinds of connectivity. To give you an analogy, imagine a sports stadium and a parking lot and a street connecting the sports stadium to the parking lot. As cars come into the parking lot, fill it up, in a little while, people start filling up the sports stadium. And then when people leave the sports stadium, a little while later, the cars depart from the parking lot. That's functional connectivity. It's a correlation. Coherence is a correlation. Looking at how as activity in one area changes, does it change in another area? How are they correlated? Cross correlations are an example of functional connectivity. Various connectivity analyses like that are functional connectivity. Now, effective connectivity is where you measure. First of all, I want to emphasize structural connectivity is the street, the stadium, and the parking lot. And that's there whether people on Earth or not. Okay, it's a physical structure. And it corresponds to the MRI. The MRI structural form is actually the same even when you die. You're dead. You can measure the MRI shortly after death, and you can't see any change. It's essentially the same. Now, with time, it will deteriorate because of deterioration of the protein lipid molecules. But the EEG is totally different when you're dead. There is no EEG. So effective connectivity is the third kind of connectivity, is where you measure the number of people going from the parking lot to the sports stadium and the number of people going from the sports stadium to the parking lot. That's effective. That's information flow, the magnitude and direction of information flow. Now, all three of these forms of connectivity are related and interdependent. So you need the structural connectivity in order for the functional connectivity to exist, but you need the EEG and the co-registration of EEG with the structural MRI to even know this. So the EEG is extremely important. I then went to the Bay Pines VA Medical Center in Florida to become the project manager for the Department of Defense program where we organized 4 VA medical centers and 3 active duty medical centers for active duty soldiers, Army, Navy, and Air Force. For them, that was Walter Reed, San Antonio, Texas for Air Force, and San Diego Balboa for the Navy. And then there's 4 VA hospitals. So we coordinated the EEG and the MRIs and the neuropsychs that were taken for all these people they had traumatic brain injury. We also had with a large group of normals too. And in the course of that, we published a variety of papers, but one we developed called magnetic electroencephalography, where if we knew what's called the T2 relaxation time, you know the details of the protein lipid, the structural integrity of the brain, the protein lipid molecules. They have to be strictly, those protein molecules have to be together. Traumatic brain injury, it scrambles those protein molecules up. Alzheimer's is one we first saw at the University of South Florida. I was a professor. Was the greater the mental deterioration in Alzheimer's and dementia in general, then the breakdown there was between the gray and the white matter in the MRI. Usually in MRI, you'll see a peak for gray matter and you'll see a peak for white matter because they have different densities of protons. The white matter, for example, is fat in it. It's myelin. That repels water. So there's less water in the white matter. The gray matter does not have fat molecules, and so you use more water in the gray matter. But they're clearly differentiated in healthy people. But Alzheimer's, no, it's just one uniform shape distribution. Now, I have a YouTube video on that. At some point, I can send you that information so people can see it. But what we're able to do, we looked at what's called T2 relaxation time, which is, in the MRI, you can count the number of protons. So what you're doing when you're looking at water, you're actually looking at the number of protons. And you put your head in a big magnet, and then around your head is it's called a head coil. It's just a wire cage. And a pulse is delivered through the wires in that wire cage to essentially knock down the protons. So the protons are like tops. And when you get into the magnetic field, they're all spinning together because it's a strong magnetic field. The stronger the magnetic field, the faster they spin. And there's actually a gradient in the MRI, so that front of your head is spinning faster than the back of your head, or the top to bottom. And that's how you actually get the slices in the MRI. In any case, this pulse is delivered through the wire. The tops are spinning like this, and then they start spinning like this, and the plane, they go down 90 degrees, and they slowly come back up. If you put a glass of water in an MRI machine, it takes 3 to 4 seconds for the protons to come back up. If you put a metal or some kind of a structured material in the MRI, the protons will relax back up in microseconds or nanoseconds. So the protein lipid molecule integrity determines how fast the relaxation time comes up. So we correlated that with power, absolute power and relative power, and with coherence and phase differences. And we confirmed 2 compartmental models, and we came up then eventually with a transfer function so that if you know the EEG, you can actually picture an MRI. So we got blank MRIs, and then we would color the MRIs depending upon the EEG. And if you know the MRI, then you know the EEG. So you can tell what the power of beta is going to be, and theta and alpha, stuff like this, just based on the structure. So there's an intimate relationship between the structural connectivity and functional connectivity and effective connectivity.
So tell me about kind of what NeuroGuide, tell me about NeuroGuide Applied Neurosciences, like how the kind of the process of like starting the company and what your guys' work is as far as kind of like applying a lot of the concepts that you previously mentioned, and sort of the way I see it, kind of applying it so clinicians, researchers can actually measure all of this stuff, you know, in real human subjects.
Yeah, well, it started for me at the Bay Pines VA Medical Center in 2001. That's when George Bush II was elected. And he's actually, you know, really, I guess in December or whenever, January 2000, and then he took office January 2001. We got word that there's efforts to the Republicans also gained control over the Congress to shift money out of our program to some other programs that they were interested in. So myself and a team of us went to Washington to testify before a subcommittee. And we presented all this great stuff, MRIs, EEG, traumatic brain injury, mild, moderate, severe, outcomes of a variety of kinds, because they're treating and helping these people. And each of us had our presentation. We were there for about 30, 40 minutes. And at the end of it, the chairman asked Dr. Salazar, do you know anything about prostate cancer? Salazar was a neurologist, worked at Walter Reed, colonel, and he knew a lot about neurology, but he didn't know anything about prostate cancer. And he asked Dr. Thatcher, do you know anything about prostate cancer? I said, no, I don't know anything about prostate cancer. I was young in those days. I still don't know much. And then, so they went on down. That basically, and he says, well, thank you very much. We really do appreciate you coming here and showing us what you've been doing. And we were dumbfounded by this. We went out in the hallway and looked at each other, and we knew that's the end of this program. These old farts, or these old guys, sorry about the language, they're interested in prostate cancer. And so, but not the brain. So I went back to Florida, and I then created Applied Neuroscience. I just went ahead and created it, registered it in case our program was terminated. And then
was that outcome really surprising for you to having presented all of that work? That must have been really surprising.
It was.
To not have it received.
I was shocked. I really was. I couldn't believe it, because we were so proud of what we had done, and there's such a need to help people with traumatic brain injury. I mean, these are our soldiers and our veterans. We need to help them. I mean, that was a passion that we all shared. And yeah, we were proud of what we had accomplished over quite a period of time, about 10 years or something like that. I don't know. It was, at that time, I joined them in 1994, so it had been about 7 years or so. Anyway, so then in June, the executive administrator at Bay Pines VA came in at 4 o'clock and said she just got word that our program was terminated effective at 5 o'clock, 1 hour. So at 1 hour notice.
Wow.
And that was really disrespectful. And so I put my resume together to think about getting a job, but I had a daughter, a 12-year-old, 11-year-old daughter at that time. And so I thought, well, we got a lot of, I had over 20,000 subjects in my database at that time. We had a lot of knowledge based upon the funding we did receive, and they didn't even care about our funding or anything. They just abandoned us. So we're able to retain our equipment and all of our databases and everything, and that was a considerable resource. So I just worked it out with the Bay Pines VA to be able to retain, and I was the principal investigator, so I had 100% control over that. And so I kept the databases and there were no problems, anything like that, and then began to create our own software to compete with existing software. And I could see that we could create a program that's superior to any of the others at that time. And the others were DOS-based, we were Windows-based. I've written programs, and Carl was an excellent programmer, so we designed NeuroGuide. So NeuroGuide took us until 2002, more or less, somewhere in that range. We didn't make any money for a couple of years, but I activated my 401ks and my retirement money, and I supported Dwayne North and myself and Carl until we could get revenues coming in and pay our bills, which we did about in 2002. And so today we have over 3,000 customers, and we're successful as a business.
Did you know that there was this sort of demand for the sort of software that you guys developed at the time that you decided to start NeuroGuide? Or did it just continue building into what it is today?
I knew there was a demand. There's no doubt about that. EEG, like you said, the brain weighs 3 pounds, consumes 20 to 40% of your blood glucose. That's not trivial. And the EEG is one of the best ways to measure that. The most inexpensive, non-invasive methods. It's just a matter of perfecting it and then really getting into what we learned at National Institutes of Health about the brain is made up of hubs and networks. So we wanted to focus using three-dimensional imaging on these hubs and then measure how these different hubs talk to each other and how they're linked to patient symptoms. But I relied upon the PET scans. Like NeuroGuide, all of the networks in NeuroGuide are just PET scans and functional MRI and SPECT scans. It's not EEG. It just happens that EEG co-registers with these imaging modalities. At the time, there wasn't a lot of three-dimensional EEG. There was some. Like I said, I was a project manager for 128-channel EEG, and I oversaw the inverse solutions that were developed, which is a way to measure. If you measure the EEG from the scalp surface, you can derive what the sources are in the interior of that surface. So imagine a balloon, for example, filled with saline that has a battery or 1 or 2 batteries in it, and you have sensors on the surface. So when you turn on that battery, as you move it closer to the surface of the balloon, you'll get a big electrical potential at the surface. And as you move it away, it gets smaller. It gets smaller, 1 over R or 1 over R squared. That's been known since the 1800s in physics. And that's called the forward solution that was developed in the 1800s. Gauss, Poisson, Laplace. And then in 1864, Clerk Maxwell put it all together for electricity and magnetism. It became the laws of the universe, basically. So called the forward solution, fundamental to physics. But the inverse solution is where you don't know where the battery is. All you know is the potentials at the surface. And then you can use an inverse solution to figure out where the battery is and whether it's oriented, or whether it's positive or negative, etc. All of that can be done by, if you do the right constraints at the surface. That was discovered by von Helmholtz in 1870. So, and it's used in cardiology at the turn of the century. You have to have, there's an infinite number of solutions, so you have to have constraints, various kinds of constraints that people test out. So at NIH, we were testing all these inverse solutions. We had epileptic patients with implanted electrodes, and you could stimulate from the tip of the electrodes, record EEG at the surface, and you could verify the accuracy of these inverse solutions. We discovered that there's two kinds of inverse solutions. One is called the discrete. That's where you take 128 channels if you want and just get 3 dipoles. That's for epilepsy. It turns out you don't need 128 channels. You can do pretty well with 32, and you do get an improvement up to 64 with that method. The other method is called the discrete method. That's where you have a dipole on all the gray matter voxels. Roberto Pascual Marquis used this in 1994. He used 2,394 voxels. So you have 2,394 little 3-dimensional vectors that are like this. You've got a resultant vector that comes out from the X, Y, and Z. And you can put that in the matrix and you can solve it. It's just linear algebra. You can solve it and you can figure out what the currents are, which resultant vector of X, Y, and Z is largest, and which voxels to account for the electrical potential at the scalp surface. So that's the distributed method. There's many different kinds of distributed methods. Loretta is only one. I have a book called Handbook of Quantitative EEG and EEG Biofeedback. I review that, and I have a table showing all the different methods. Loretta had some advantages over others, but the others were pretty good. Now, the problem was that everybody used it's called a lead field. It's essentially, in order to solve the inverse solution, you have to guess about what's conductivity inside the balloon. How much kind of resistance or conductivity changes there with the skull, the scalp, the ventricles, the white matter, gray matter, if you can. The more information you have there, the better you can, the more accurate your inverse solution. The problem is people used a spherical head model. So it's basically get a sphere and you shrink it around the head. And that works pretty good for the crown, the crest up here. But for the temporal lobes, it doesn't work very well as 2 or 3 centimeter error, because the brain is actually shaped like a loaf of bread. It's flat on the bottom and it's elongated. It's not spherical. And so at NIH, we used also what's called the boundary element method and the finite element method. The boundary element method, when you sit down in a computer and you actually click on the boundaries of the MRI. It's the real shape of the brain, the realistic head model it's called. It's not some abstract sphere. Now, when you use that, you suddenly have this improved accuracy in the inverse solution. The problem in those days was that we have to send the data out to a supercomputer, and it takes like a day or two to come back with the solutions. And so the spherical head model was very useful. But the boundary element method actually is much faster. So the finite element just takes too long. So we use the boundary element method, and so that's what we use today. We use the boundary element method, which improves the accuracy, and also Ernesto Soler, who's one of our employees, in 2007, he developed what's called SW Loretta. So Loretta is called low resolution electromagnetic tomography. And its resolution, even with 128 channels, you can't get less than 1 centimeter. Very difficult. There's a few examples, but they're very rare. And also, it turns out that these Broadband areas are larger than 1 centimeter, so you don't need less than 1 centimeter. They're 2 or 3 centimeters. It's large collections. You got 100 billion neurons, and at any given instant of time, there'll be a billion here in one Broadband area, and 5 billion in another one, and another 5 billion over here, and 2 billion there. That they get synchronized for 200 milliseconds. 200 milliseconds. That's how the brain does that. It has a shout out, so who's available. It synchronizes what resource there is in these hubs. They mediate a given function, it releases those several billions of neurons, and then has another shout out, who's available. And it just keeps doing this. Called a phase shift. There's a shout out, and the phase lock locks them in to mediate a function for 200 milliseconds. If they get locked in too long, now autistic children have this problem. There's not enough resource the next moment of time. Or if you don't have a big enough shout out. If you get a big shout out, then the larger the phase shift duration, the longer the shout out, then the higher the IQ. So we published that. So it has real functional meaning. So the resolution of the distributed solution always is less important than the just general accuracy for the center of these the boxes. At the same time, we were working with magnetism. Magnetism is 1,500 times weaker than electricity. So you have to have a $2 million shoulder cage and a 15-ton cage. At NIH, we would have the train schedule on the side of the shielded room, because when a train would go by a mile away, it would create so much artifact that you couldn't measure magnetism. So that's the problem with magnetism. It's very expensive, it's very weak, very important. It's different. It's at right angles to the electrical field that Maxwell discovered. In any case, if you, the good thing about the magnetism is this heterogeneous tissue space is invisible to magnetism. So the ventricles, the gray matter, the white matter, the blood vessels, all of that is invisible to magnetism, but not electricity. Electricity, it's like a resistor in a circuit. It blocks it, it distorts the flow of electricity. So Ernesto found out a way to make the lead field and the balloon, the interior of the balloon, completely homogeneous, just like magnetism. So now electricity and magnetism are the same, and that allows us to image the cerebellum with high accuracy. The red nucleus, the thalamus, the subthalamus, the habenula, the nucleus accumbens, these really fundamental hubs, we can now image. And that's what our NeuroNavigator does. So we spend a lot of time perfecting that, finding ways to apply that to the Parkinson's patients, let's say, or drug addiction is an example. The dopaminergic system, dopamine is manufactured in what's part of the brainstem called the ventral tegmentum, and then it's transported to the nucleus accumbens, which is in the striatum, it's anterior, below the cortex. And then that's distributed from the nucleus accumbens to a variety of areas, the amygdala, the nucleus accumbens, in a lot of places, because it reinforces the number and size of synapses. That's what dopamine does. So it predicts a future reward too. If there's a prediction of future reward, dopamine surges out. If there's confirmation of that reward by your actions, etc., then you'll change the size and number of synapses. Eric Kandel got a Nobel Prize for doing that, showing that happens with biofeedback. That literally is what neurofeedback does. It changes the size and number of synapses. However, if you make an error, and you screw up in your movements, then the habenula suppresses the dopamine. That way you won't keep doing stupid things. Let's say you're looking for your toaster and it's in a cupboard. You think it's in a cupboard to your left side of your sink, and your prediction of a future reward starts going up as you take action to open the cupboard to discover that, the dopamine surging up. But lo and behold, there is no toaster. It's actually in the other cupboard to the right of the sink. Well, the habenula is going to suppress the dopamine right away, so you don't keep opening up the left cupboard all of that. So that's how it works. But that's distorted in drug addiction cases, a variety of kinds. So we can image those and measure those two hubs with respect to a healthy group of age-matched individuals. And we can see if there's dysregulation there and begin to do neurofeedback directly on the nucleus accumbens and the habenula to try to restore the stability and efficiency of those hubs. That's just one example. But having the knowledge of the brain, being able to image it structurally, with functional connectivity, effective connectivity, and link that to the symptoms, now you can target the parts of the organ that are not working right. That's one of the amazing things about the field of biofeedback. People don't really understand the organ that they're working with, or even the neurology and psychiatry. The brain is a little bit of an orphan between these two competing disciplines. But in cardiology, for example, the cardiologist knows the heart. They know if the left ventricle or right auricle or the mitral valve or some other valve isn't working right, or the conduction velocities and this fibrillation, etc. They know with this, and now they start working with those parts of the heart to make sure that it works right. But not the brain. When it comes down to, you put one electrode up here, the whole brain is being measured. You're not getting at the hubs in the networks. You actually have to do three-dimensional imaging of the brain and then target those hubs known to be linked to the symptoms.
So tell me about the report that NeuroGuide, at least from what I've seen, it gives you a lot of information. There's information regarding like the Z-scores, sort of the standardized scores, raw data, power. I mean, there's so much information. How do you go about, do you have a process, as far as looking at one thing first and then moving on to the next thing, or does it vary case by case? I just wanted to hear your process in sort of going through all of this different data.
Yeah, the process is the same that's actually used in cardiology and a lot of medicine. You start with the patient's symptoms. It could be tachycardia, it could be dizziness, and you may be able to find that one of the valves is leaking, etc. But you really want to work with the symptoms. And so if somebody has anxiety disorder, first of all, you do a careful assessment of the patient's clinical history. Which things are most troublesome? So there may be anxiety, attention problems, history of attention. It could be that the attention disorder is causing the anxiety. At the soldiers at Fort Campbell, they back from Afghanistan, they have PTSD. So you evaluate the PTSD. Somebody in an automobile accident, they've got the characteristics of traumatic brain injury. Now you look at the networks known to be affected by traumatic brain injury. So you start with the symptoms, and let's say it's PTSD as an example. Well, we know that PTSD is related to the amygdala bilaterally. That's in PET scans, functional MRI, and anatomical studies. The anterior cingulate gyrus, the frontal lobes are supposed to regulate the amygdala, and the insula is regulating the autonomic nervous system in coordination through the limbic manifold. And it's affected also by PTSD. So we look at those known hubs known to be related to PTSD. And we say, aha, the amygdala is 5 standard deviations outside of normal. Cingulate gyrus is all right. It's 1 standard deviation. And you can see the spontaneous, because what happens, like Bert Kendall showed, if there's a life-threatening event, there'll be this sudden proliferation of synapses on the lateral surface of the amygdala. Okay? Now you're stuck with this dysregulated amygdala, so you're in a state of anxiety and stress and fear all the time. Soldiers come back, they can't go to 7-Eleven or Walgreens, or they don't sleep very well, and they don't get along well with their spouses and their family. But at Fort Campbell, they target the amygdala, the insula, the anterior cingulate gyrus, and the frontal lobes. and reinforce them towards greater stability and efficiency. And they get in one day, sometimes two, they can start sleeping. And now they're starting to go to 7-Eleven and Walmart. And this is, they give 10 Loretta neurofeedback sessions. It's spread over a period of time because they're there for 90 days for the rehab. But they give other rehabilitation too. But that's a fundamental part of their protocol. It's a standard protocol. That's just an example. If it's anxiety, you look at the anxiety network. If it's memory, you look at the hippocampus. And you look at the memory networks. And you see, yeah, there's 5, 6, 7, 10 standard deviations out. So you move it towards greater stability. And you plot how well the brain is moving towards greater stability, as well as look at the severity of the symptoms. So you want the symptoms to go down along with this improvement to stability and efficiency of the brain. So that basically is the procedure. You start with symptoms, you link the symptoms to the patient's brain to dysregulation in hubs. You then have a protocol to target those hubs to reinforce them towards the center of a healthy group of individuals. That's what Z-scores are. It's just simply a reference database similar to a blood test with your blood constituents. It could be your hematocrits or your white blood cell count or whatever. It's being compared to a healthy reference database, these blood test kits. And then you do what you can to move those hematocrits in the right direction.
I wanted to ask you about sort of the Z-score database. Do you see a need, or do you think it would be helpful to ever sort of get a database of, say, like peak performers, people with exceptional brains, and then be able to sort of train people towards that rather than kind of the standardized, just like average brain, or like, do you see it differently than that?
No, we do. We actually have that. We have a very large database that ranges in IQ with a variety of different people. They're all healthy, but we do have peak performers. So we take people with 120 IQ and higher. And we also take most of these are a variety of different people, but we work with the Army at various bases, and they have these colonels, they have these really high working and special ops, really high quality functioning individuals, both athletically and personally, intellectually. We have top-notch businessmen, and we put them together as our peak performer reference. And we put them in a dial. And we also measured all their hubs, all their networks, the anxiety network, the attention network, the memory network, etc., default network. And we put them into a dial. So they're at one end of the dial, and wherever you come in, you'll be an arrow. And you keep reinforcing those, each of the networks is represented by a dial. And so you're moving those networks in the direction of the peak performance. So you have a target being the exceptional ones. Because you find that like in athletics, people will have attention problems. They may be peak performers in their ability to run, but when you're at the plate, or if you're a pitcher, you have to concentrate. You make one mistake, and the ball's over the right field wall. So attention is there important. There's a lot of these components giving rise to peak performance. So it isn't just it's a nice buzzword, but it's you really need to know, well, what is it you want to be? If you're going to shoot an arrow, you have problems because you're jiggling, and that could be the cerebellum and the Parkinson's network, etc. So you need to kind of drill down and then move them in the direction of that really peak performing group.
Right. And I wanted to ask you also about when it comes to sort of modifying brain activity. You know, we touched on, you discussed neurofeedback a bit. What's your take on technologies like transcranial stimulation, the different types of stimulation, along with like pulsed electromagnetic therapy?
Well, those are useful. But they should be combined with neurofeedback because they don't create new synapses. They just kind of create a temporary scrambling of the networks. It's a little bit like what happens in the brain. The loops in the brain are dynamically organized in such a way there's compensatory dynamics and weak systems, but they're sharing information all the time to create a homeostatic outcome that's positive for the individual. And when you put in pulsed electromagnetism or direct cortical stimulation, TDCS, you disrupt the habits of the loops. Neurons get in a habit. They go round and round and round these loops. And now suddenly the synapses are getting this unusual input into them that is not physiologically like it normally is. And they then will start searching around. Actually, they'll depart. Groups of them will depart from that habitual set of loops. But within an hour or so, they come right back to where they were. They're not going to stay outside of the regular orbit unless you add dopamine or serotonin or something that's going to change the size and number of synapses in subset of neurons, so they will stay outside of that habit, or they'll establish a new variation of the loop, and it's permanent. Dirk de Ritter gave a really great talk at ISNR 3 years ago or so, where he spent a lot of time. He's a neurosurgeon, and he worked a lot with tinnitus, and he compared pulsed magnetic stimulation to TDCS, and I think ADCS, and then neurofeedback in tinnitus. And he found with pulsed magnetic stimulation, he can get a little change. He can get a change and a smaller percentage than neurofeedback, but it would be temporary. By the next day, the tinnitus would return. And he found that with all of those methods. But neurofeedback, it would be months and months. In fact, even a year, he showed a year or two afterwards, the tinnitus in these patients is still gone. But not with pulse magnetic stimulation, not with TDCS. And then he showed if you can combine the two. So you do TDCS first, and in one session, the next session, it takes like 10, 20 minutes of pulse stimulation, and then you just do neurofeedback. And he found that was a little bit better than just neurofeedback by itself. So, so they're all important, but you got to recognize you don't change synapses when you stimulate the brain that way.
So so with neurofeedback, you see the main, do you see the main benefit or the way that it works is by creating these new synapses compared to, I guess, like modifying like the electrical rhythms of the brain? I guess they're intertwined. But how do you sort of see that?
Well, first of all, Eric Tyndall got a Nobel Prize. So yeah, man, if you read the stuff he did to drill down on exactly how biofeedback changes the size and number of synapses. So essentially what he did that in invertebrates first I was working at Albert Einstein College of Medicine at the time as a postdoc and went to his lectures. He was doing really great work because you can actually see the molecular mechanism when cytokines would go up through tubules and neurons up to the RNA, activate the RNA, DNA circuits that would create these other chemicals that would transport it back and change the size and number of the synapses. So, and that was well established in aplasia and other invertebrates, but especially aplasia. But it wasn't worthy of a Nobel Prize at that time until people started doing the same things in vertebrates, in cats and rats, and eventually humans. And when that happened, he was awarded the Nobel Prize in the year 2000. So he nailed it down. That is what it does. There's no, as far as the rhythms are based, but first of all, a pyramidal neuron will oscillate at all rhythms without changing its synapses. You take a pyramidal neuron, out of the brain, put it in a petri dish, which people would do at Albert Einstein College of Medicine, and you change the polarization level of the neuron. You inject currents into it so it will become more depolarized. And you're putting an input into the synapses, but the neuron will oscillate faster and faster and faster and faster the more depolarized it is. But there's no actual change in the synapses. So the excitability of different circuits will determine what their frequencies are. But the frequency is much less important than the location. So since all locations are going to oscillate at all frequencies, if you look at one location, let's say it's the hippocampus with somebody who has memory problems, well, that may be dysregulated in a variety of frequencies. Just one, you can't attribute it to a frequency, it's the location. And the hippocampus may not be talking to the amygdala like it should, or to the thalamus or the medial frontal lobes like it should. So the connectivity is what the problem is between these two locations. So independent of frequency. So frequency is really not important. What's important is location, location, location.
So my question for you, how does someone go about, I mean, it seems like this is such sort of a specialized sort of, you need so much understanding of all of these different sort of metrics of measuring, the brain. For someone going, to neurofeedback, like, do you see a problem with like neurofeedback practitioners not being aware of all of this stuff, and potentially being able, like, to actually, like, do you think neurofeedback at times can actually make the brain worse, or is that not how you perceive it?
Well, there's one person, Corey Hammond, that claims that there may be, but it made people worse. But most of what he talks about is anecdotal. I was hired by United Healthcare as a consultant, and they did, and FDA did too. They did a 10, 20-year survey of the literature of biofeedback looking for adverse effects. For them, an adverse effect is something that's really serious. It's not, you get somebody that's got some kind of problem comes in, and after biofeedback, they say they have a headache. So that's, and then they're fine in an hour or two or for a day. That's not to NIH, to FDA, or to United Healthcare a serious adverse effect. For them, is where people lose limbs, they die. They have serious impediments and all kinds of things. I mean, throughout medicine, that's really what they're concerned about. Anyway, so United Healthcare forgot that they did a vast survey. They had this whole system looking for adverse effects, and they failed to find any adverse effects. The only thing they found was Corey Hammond's paper, and they said, well, that's so anecdotal, it's just opinion. Apparently it's opinion. Doesn't mean anything, and if there's just one paper out of thousands, and they can't find anything, they concluded there are no sufficient adverse effects. The FDA did too, okay? And as a consequence, I think it was around 2009, FDA said, you no longer have to register, have a 510K to do neurofeedback because they failed to find any adverse effects. And the real question is why? You think there would be adverse effects? That's what they asked me. It says, Dr. Thatcher, why do you think there aren't any adverse effects? You're changing the brain. You got a Nobel Prize for Kandel. What's going on here? My hypothesis is that essentially there's compensatory systems and there's weak systems. Okay, they're both operating together. But the compensatory systems and the overall dynamic between these hubs is homeostasis. It's to maintain efficient communication and stability in the dynamics in order to have a positive outcome, which is wired into our brains to be able to perceive a color is blue when it is blue, and to be able to take action when a mountain lion jumps through your window. So all of that's got to be done, and but it does it with the help of others, so to speak. So, and your frontal lobes are going to help with the visual cortex a bit. I mean, there's that sharing that's going on all the time. So the compensatory dynamics are very resistant to change, essentially is what it is. It's the weak ones that will change. And so if you can target the weak ones, and this is common in neurology, that's what you do, like you do the cerebellar tests, etc., like left and right. They look for the weak thing. You're doing your left and right hands, and they got all these tests. You look for the weak aspect of the cerebellar circuits, and then you treat that weak system. It's the same kind of idea. And you won't know if it's weak unless you look at the comparison to z-scores, because a lot of the compensatory systems are actually just healthy. They stay within 1 standard deviation. Some of them will be out 2 or 3 standard deviations, but if it's a network, like if somebody has an anxiety problem, you look at the anxiety network. You're not going to be looking at the cerebellar network. You're going to be looking at the anxiety network. So right away, you're limiting the universe of things you're going to look at because it's linked to the symptoms. And then you'll see the hubs in there are deviant. Some of them, not all of them, are deviant from normal. You target all of them to move the direction of z equals 0 in the center. And you'll find the weak ones will just start moving, and then the compensatory ones will move too towards greater stability. So all of them move in the direction of stability without adverse effects, and it's not difficult. You just really all you got to know is the symptoms, and then you click. You just anxiety. Okay, you click the anxiety network, and then you click go, and you start doing your feedback on the anxiety network. It's a memory problem. You say memory, go. Now you're doing the memory network. So we teach people to do this. It's quite easy to do. The hard part is getting electrodes on and getting good recordings and making sure you don't have any artifact and you got recording hygiene. So that's a mechanical thing. You got to be able to recognize what's healthy EEG and what's not artifact. You don't have to worry about categorizing different kinds of artifact. I was board certified in conventional EEG, and like half the exam is trying to distinguish an eye blink from an eye movement, from a tongue movement versus a head movement. And you really don't care because you want to recognize the EEG because it's much weaker. It's microvolts, whereas artifact is millivolts. So you just want to see what's healthy EEG. So you got to train people to do that. And the other great thing about EEG is it's highly reproducible because in the resting state, it's being produced by all these loops. These are hardwired loops. And so if you take, and the literature shows this, if you do a search in the National Library of Medicine on EEG and reliability, or EEG and test reliability, you'll find over 5,000 publications. Almost all of them show 0.9 and higher if it's artifact free. And if you take 20 seconds of EEG, it's about, and then another 20 seconds of EEG, the first 20 seconds will predict the second 20 seconds at 0.85. 40 seconds will predict another 40 seconds somewhere in the record at 0.9. And 60 seconds is 0.95. 2 minutes is 0.95. 3 minutes is 0.95 because it asymptotes roughly at 0.9, 0.98, 0.95. So if we say get at least 2 minutes of EEG and then test, you have test reliability. Make sure you get above 0.9. So 5 minutes of EEG, you can take, we have methods to take multiple 1 or 2 minute samples and show that you got the asymptote of 0.9, 0.95, and then show you get the same clinical interpretations no matter what you select, as long as it's not artifact. Then you'll get the same. And you can do all that in 1 or 2 minutes, but you need to go through that step to make sure you get good quality data. Otherwise, you're wasting the patient's time, your time. There's no reason not to do that. And also, you should never use independent components analysis. People are doing that at NIH. That was developed actually it was developed by the Russians in the 1950s to identify, to separate voices in a room. So if you have 10 people in a room, you have 10 microphones around the room, you can separate out, because everybody's voice is different than everybody else's. You can separate out, it's called blind source separation. through independent components analysis. But what was applied to evoked potentials in the 1990s, mid-1990s, was independent components analysis, in which the assumptions don't apply very well to EEG, because the assumption is that the components are truly independent, essentially that they're noise. But the brain, parts of the brain are not independent. Every part of the brain is talking to every other part of the brain. It's just simply the way it's wired. With evoked potentials, you don't really care about the functional connectivity or effective connectivity. So they thought maybe this is a way to get rid of artifact. It does affect the amplitude of the evoked potential, but they really don't care about that. Anyway, so now with EEG, MITSAR, when EEG and MITSAR decided to use it to do artifact rejection. And it doesn't, I actually reject artifacts. Essentially what you do is, let's say you have 19 channels of EEG, and you got, let's say, 5 minutes of EEG, and you got 30 seconds of blinking your eyes at different parts of the record. So rather than select the artifact-free parts, what they do is they decompose the entire 5 minutes into 19 independent components. And they say, well, this one component seems to be loading on an eye movement. And so is this one too. Yeah. So this third one is an eye movement too. So now you'll take 16 components and recreate a 19 channel digital time series. Then you replace the patient's EEG without the patient's knowledge or consent, right, with this bastardized, digitized time series. It's not their EEG. And if you compare the person's real EEG to this digitized replacement, they don't even look like each other. It's like a different human being. And you don't have any, the phase differences are all scrambled. So essentially what's going on is you actually did not remove the artifact. You just smeared the artifact, that 30 seconds of artifact, over the whole 5 minutes. That's literally what goes on. In order to smear it, and visually it looks pretty good, you have to scramble up the phases. You get them to all kinds of going this way and that way and this way, and they get down to zero. And there's no coherence, there's no functional connectivity, there's no effective connectivity. And it's just simply, it's unnecessary to replace a person's EEG. It actually takes more time to do that because you have to identify the component, you got to then run it through. We have methods that, as long as you get artifact-free data, I mean, we can use that as a template to get more artifact-free data without no replacement. You just take the real digital data and just replicate it, make sure you get the same clinical conclusions. So we just had a paper accepted in the Journal of Neurology and Neurobiology showing how independent components analysis replacement is just artifact. It doesn't remove artifact, it actually produces artifact.
Interesting. Well, Dr. Thatcher, we're coming up onto the end of the show, but before we end, I wanted to get your take on where you see kind of all of this research and this whole kind of field going, because it seems like there's still a lot of divisions between, I mean, psychiatry and neurology. They're definitely not at all, integrated. And seems like often, clinicians, are kind of they're sort of contradicting each other. So where do you see all of this going? Do you see there becoming more of like an integration between psychiatry and neurology with all of these different electrical recordings and analyses, or how do you see the field kind of going from here?
Well, yes, I do. I mean, I'm not sure that ISNR is the organization that's capable of doing that. It's got its own political factions, and it's not very scientific. And people don't want to link symptoms to the patient's brain. I mean, usually people do, but if you have they would never survive as cardiologists because you've got to link the symptoms to the heart. And you're taught that. but people are simply not taught to link symptoms to the brain, at least in the ISNR community. But there's a Society for Human Brain Mapping and Therapeutics. These are neurosurgeons, neurologists, physicists, engineers, and they're not biased. They want to link symptoms to the brain. And so actually, I'm putting together a position paper. I was writing when you called me for tomorrow's presentation I'm on the board of the Human Brain Mapping Program. And we're going to make this presentation to the congressional presentation for more reimbursement. And to make the presentation that modern neuroscience now is able to image the brain like it never could before, and it's inexpensive. And it can be done remotely now with the COVID-19. You can connect up. We have one neuropsychologist who has 30 different locations. He's has his patients measuring the EEG, so they don't come into his office, and they can do it remotely through TeamViewer, GoToMeeting, Zoom, etc. And so, applying these new technologies to help patients that have PTSD or Parkinson's disorder or anxiety disorders or balance problems or addiction problems is something that we can do if we get enlightened people, educate people to kind of move off their squares and actually try it out. So you have to have education. The science is very solid. There's over 150,000 peer-reviewed journal articles on quantitative EEG. And so the opposition is primarily the neurologists who only believe in visually looking at squiggles. They don't like using a computer. They argue it's unreliable, even though literature doesn't say that. So I have to make the case. Here's the opposition. This is what they say, and here's how we handle that. And so anyway, there's that. Then there's another. I've been asked to put together a curriculum for the Carrick Institute. There's our 2,000 functional medicine doctors and chiropractors. They're asking for this. They're asking to get education on quantitative EEG and EEG biofeedback. And they approached me because they know about my approach, being looking at the brain, the parts of the brain that are not working right, and then trying to move them in the direction of greater health. To them, that makes common sense. As a chiropractor, that's what you do. If you have a muscle group that's not right or is imbalanced in your spine, well, you straighten it out. It's just the history of biofeedback where you just put one electrode up here, or you do theta-beta ratio, and you do the randomized double-blind studies to try to convince drug companies, and you keep, there's about 10 or 20 of them already, and all the drug companies say, so, well, give me another 10 or 20. I'll spend another 10 years until we can see another 10 or 20. Spend a few more million. And then after 10 or 20 years, well, we want 10 or 20 more, you know. That's how I do, because it's really, I'm not sure why. It's unnecessary because 95% of medicine is not double-blind randomized control study. Anyway, that burden is something that's not relevant as long as it doesn't get politically overburdened. Instead, you move patients towards greater health. When people are going towards greater health, insurance companies reimburse for it, okay? And the practitioner benefits because they get more referrals. So the key to it is getting people healthy, whatever the problem is, using inexpensive, non-invasive methods, and then eventually through education, this will work. So we also have put together a certification body. And we've been asked, like I said, to get a curriculum really for both of these societies. Together, they're about 4,000 or 5,000 people. ISNR is 300, 400. So our strategy is we got an exam, we've got things organized so that it's a virtual exam, and they have to watch our videos. We have about 40 videos, and they have to answer questions, and then they get a certificate. And basically that's what we're going to be doing to help the field.
Awesome. Well, Dr. Thatcher, if people are were interested, in any of the sort of stuff that we discussed, where would be the best place or places for them to visit? What sort of resources would you direct them towards?
Just go to www.appliedneuroscience.com. That will get you started. There's a whole bunch of submenus. There's scientific literature. There's places to order, but there's also ways to get in contact with our staff that will do mentoring and explain things and teach people. And we have 4 full-time people, myself included, that help educate, get people going. So that's the best. We also have NeuroLink, ANIneurolink.com. That's our new product that's on a smartphone, where people can link their symptoms, the severity of the symptoms by self-report to the hubs in the brain. It's a free app. It's Android and iPhone. And then they send that information to the clinician. So the clinician can see, when the anxiety network is deviant from normal, you can immediately have a protocol. And then the clinicians, we have radar maps and line bar graphs to show how the severity of the symptoms declines as a function of treatment. So it's a combination of things that we're doing all of that.
Great. Well, Dr. Thatcher, it was an honor to have you on the show. Thank you for all your contributions to the field. For those listeners who enjoyed the show today, go ahead and like and subscribe to our YouTube channel. We're Roscoe's Wetsuit. And you can also find audio versions of the podcast available on Spotify, Apple Podcasts, Stitcher, and just about anywhere else you can find podcasts located. Also, we're launching Roscoe's Wetsuit Premium, which you can find at patreon.com/Roscoe's Wetsuit. There's going to be some cool exclusive content and videos on there. More to come about that shortly. Dr. Thatcher, again, thank you so much for coming on the show today.
Thank you, Toby. It's very helpful. I appreciate it.
Absolutely.